Hey guys, in today's video, I'm going to be going over the review problems I gave you guys last week in an effort to study for quiz 1 review. So let's hop right into it because otherwise my videos tend to get really long and I don't want that for you guys. So here is our first problem solve, this equation check for extraneous solutions. We have an absolute value problem. The absolute value of a plus 3 is equal to 1. If you remember our 3 steps to solving absolute values, is step 1 is make sure that the absolute value is completely isolated. In this instance, it is. So we're going to go ahead and move on to step 2. The reason I know that this is isolated is because the absolute value is the only thing on the side, on the left-hand side of the equation, and everything else is on the right. So I'm going to do my positive case. Since it's an absolute value, there's 2 bars, meaning 2 solutions, 2 potential solutions, meaning 2 answers. We're going to do a plus 3 is equal to 1 and solve for a. Subtracting 3 from both sides, I end up with a is equal to -2 as my positive solution. And doing my negative solution, I have a plus 3 is equal to -1. Subtract 3 on both sides, you get a is equal to -4. So step 2 is complete. I considered both cases and solved accordingly. Step 3 was to check your solutions in the original problem, and my advice was to write the problem exactly as is, but anywhere that there was a variable, you're going to put a set of parentheses. It just helps us to figure out like where to plug the next corresponding value in. So I'm going to check -4 first, just because I read things from left to right. So that seems to be the first equation on the left. So then absolute values can act and behave just like parentheses. So let's simplify what's inside. -4 plus 3 is -1 with our absolute value. Is the absolute value of -1 equal to 1? Why, it sure is, because absolute values turn everything into positives. So a is equal to -4 is definitely one of our solutions. Let's check the next one by rewriting our problem and plugging in our second option, -2. Again, we're going to simplify inside the absolute values. -2 plus 3 simplifies to 1, and it still has absolute value bars. Is the absolute value of 1 equal to 1? Heck yeah, it is. So I have a is equal to -4, and a is equal to -2 as my solutions. Or you can write it as a is equal to -4, comma, -2. Put both answers in the curly braces. The smaller value, the smaller number comes first. -4 is smaller than -2. Nice. Let's do the second one. All right, absolute value of -4a plus 1 is equal to 1. Step 1 says isolate the absolute value on one side of the equation. My absolute value is the only thing on the left. So I can move into step 2, which is to consider my positive case and my negative case. My positive case is -4 times a plus 1 is equal to 1. I want to solve for a, so I'm going to subtract 1 from both sides. I have -4a equals 0. And I still need to get a alone, so I'm going to divide by -4 on both sides. Whatever I do to one side, I have to do to the other. Now remember, it is okay to have 0 on the numerator. It is not okay to have 0 in the denominator. So 0 divided by -4 is 0. Let's consider our negative case. -4a plus 1 is equal to -1. Nothing inside the absolute value changes because absolute values are always positive. We're going to solve for a, so we're going to subtract 1 on both sides. -4a equals -2. I'm going to divide both sides by -4 again. To get a is equal to 2/4. A negative divided by a negative is a positive, or I can reduce this to 1/2. Step 2 is complete. Step 3 said to check my solutions for extraneous. We don't want any liars up in here. -4, wherever the parentheses or wherever our variable is, let's put a set of parentheses there. +1, is that equal to 1? And because I like to read left to right, I'm going to put 1/2 in here first, just for funsies. Again, we're going to simplify inside the absolute values first. So for -4 times 1/2, or -4 divided by 2, right? I could do this, -4 divided by 2 plus 1. We want to know if that's equal to 1. And -4 divided by 2 becomes just -2. And -2 plus 1 becomes -1. And the absolute value of -1 is 1. So that guy works out. 1/2 is certainly a solution. Achoo. Excuse me. Let's check the second solution. -4 times a plus 1 is equal to 1. But for a, we're going to substitute in 0. Simplify inside the parentheses. Anything times 0 is 0. So I just have 0 plus 1. Is that equal to 1? Is the absolute value of 1 equal to 1? It sure is. So a is equal to 0 is also a solution. So I can say a is equal to 1/2 and 0, or I can say a is equal to 0, comma 1/2 inside of my curly braces, denoting that both of those solutions satisfy this absolute value. Remember, the smaller number comes first. Problem number 3, the absolute value of 4 plus 7b is equal to 0. Again, is this guy completely isolated? We have to always check. Yep, that's the only thing on the left-hand side. So now we can proceed to step 2, which is to consider the positive case and the negative case. Positive case is 4 plus 7b is equal to 0. And let's think about this for a quick second. 0 is the only thing on the right-hand side, like just 0. That's the only thing. But the reason 0 was invented was to keep the positive numbers and the negative numbers, like to separate them. And then we decided to put 0 smack dab in the middle. So actually 0 is neither positive nor negative, simply by design of why we invented the number 0, right? We needed something to be a placeholder, but it's neither positive nor negative. It just separates those two types of numbers. So really, we're only going to have to solve 1. It doesn't make sense to set up my negative side of the equation. 4 plus 7b is equal to 0 is the same thing, because 0 is not positive nor negative. So really, we're just solving one equation right now. So to solve for b is the variable in this instance. We will subtract 4 from both sides. And I get 7b equals -4. Divide by 7. We get b is equal to -4 divided by 7. And that's it. And you can see why, because if you didn't believe me, I could still subtract 4. I end up with the same problem on the left. 7b equals -4, divide by 7, divide by 7. You get b equals -4/7. It's really just the same value. Step 2 is complete. We still need to check for extraneous solutions. So we have 4 plus 7 times b, our variable, equals 0. And now we're going to just check -4/7. So again, simplifying the inside, I have 4 plus 7 over 1 times -4 over 7. You can see that those two are going to cancel. Is equal to 0, or not cancel. 7 divided by 7 is just equivalent to 1. So now I have 4 plus -4. Is that equal to 0? And 4 plus -4 does, in fact, give us 0. And the absolute value of 0 is 0. So b is equal to 4/7. -4/7 is our solution. Or you could still say b is equal to -4 over 7. But that would be the only number inside our curly braces, inside our set notation. Let's do the next problem. Oh, 8 plus the absolute value of 7 plus 6b is equal to 25. Slightly more exciting. For step 1, make sure the absolute value is isolated. Since there's an 8 plus on the left-hand side, we need to get rid of that 8 plus. So this is saying 8 is being added to the absolute value of 7 plus 6b, and that this is equal to 25. So let's undo this 8 right here. So how to undo a positive 8 is we'll just subtract 8. We have the absolute value of 7 plus 6b is equal to 25 minus 8, and that gives us 17 here. Now step 1 is officially complete, and I can move on to step 2, which is considering my positive case and my negative case. I like to start off on a positive. 7 plus 6b is equal to 17. We want to solve for b here, so let's use SADMEP. Can we add or subtract, multiply or divide? So I have 6b is equal to 10. We're going to divide by 6 to get b alone. We end up with b is equal to 5 over 3 is how we can reduce that fraction. 10 is divisible by 2, gives us 5. 6 is divisible by 2, gives us 3. Our negative case is going to be 7 plus 6b is equal to negative 7. We're going to subtract 7 from both sides. If 6b equals negative 14, we end up with b is equal to negative 14 divided by 6 can be, oh, I made a mistake. Oopsies. This should be negative 17. My bad. So negative 17 minus 7 is negative 24. Oops, that's okay. Negative 24. And we're going to divide negative 24 by 6, and that gives us negative 4. Negative 4. Always double check. That does tend to happen to us when we move too fast. So learn from my mistakes. Mistakes are totally normal, but that's why proofreading and going over your problems is really important to just verify. It's not unusual to get a fraction, as we can see in the positive case, but just always double check. Cool, now let's check them in our original equation. 8 plus the absolute value of 7 plus 6 times b is equal to 25. I like to read from left to right, so I'm going to plug in negative 4 first. And the absolute value behaves like a parenthesis, so I'm going to simplify what's inside my absolute value first. So 6 times negative 4 is 24. I have 7 minus 24, essentially. And then 8 plus that value. And I want to know if that's 25. And 7 minus 24 is negative 17. So I have 8 plus the absolute value of negative 17, and I want to know if that's equal to 25. But the absolute value of negative 17 is just positive 17. So 8 plus 17, is that equal to 25? Yes, it is. So negative 4 is certainly a solution. Now I'm going to plug in 5/3 is 8 plus the absolute value of 7 plus 6 times b equal to 25. And I'm going to plug in 5 divided by 3. Again, we're going to simplify this inside here first. So I still have 8 plus the absolute value of 7. 6 times 5 is 30 divided by 2. Oops. 30 divided by 3, I'm sorry. That gives us 10. So now we are at 8 plus the absolute value of positive 17, is that equal to 25? The absolute value of positive 17 is going to be 17 as well. And I want to know if 8 plus 17 is 25. As a matter of fact, it is. Yay! So 5/3 is also a solution. And if you want to be fancy and write your answers in your set builder notation, knock yourself out. It's going to be the smallest number first, -4, and then the next number second, 5/3. All right, let's keep moving and grooving. Why not? Problem number 5, -4 minus the absolute value of -4 minus absolute value 4 minus k is equal to 12. So again, we want to isolate our absolute value. That's what step 1 is, okay? So this says the number -4, and then there's a minus in front. And if this was parentheses, you guys would understand that that's being like -1 times that quantity, right? So this is a little bit of invisible math. Let's make sure that we go in there and we don't trick ourselves. We realize that this is -1 being multiplied by our absolute value. So again, we're going to want to use PEMDAS backwards when we want to isolate. So that's SADMEP moving this way. Is there anything we can subtract or add first, then divide or multiplied to get our parentheses or our absolute value in this case alone? So in order to do that, we're going to undo -4. We're going to add 4 to both sides. I can't subtract anything right now, but I can add. So this leaves me with -1 times the absolute value of 4 minus k equals -12 plus 4 is -8. Now I want to know if I can divide or multiply both sides by something to get rid of that pesky negative on the left-hand side. And I could multiply or divide, whatever floats your boat. I just like to divide since I know that's multiplication. So I'm going to have 4 minus k inside of an absolute value is equal to 8. Okay, now I'm back to where I am. I'm done with step 1, and I consider my positive case for step 2 and my negative case. 4 minus k is equal to 8 is my positive case. Subtract 4, I get -k equals 4. Divide both sides by -1 or multiply, whatever your heart desires, and you get k equals -4. For my negative case, 4 minus k equals -8 is my situation. We're going to subtract -4 on both sides. I have -k is equal to -12. So dividing both sides by -1 or multiplying both sides by -1, I get k equals +12. Then step 3 says to check your solution. Check it out. Check your solution in the original. -4 minus absolute value 4 minus variable equals -12. Be very careful when you have a complicated problem like this that you're writing it down verbatim each and every single time. I personally have made too many mistakes where I accidentally mess up and then it throws me off thinking I have an extraneous solution when I actually do not. I'm going to plug in the negative case first, 12, just to see. Again, let's simplify the inside of our parentheses first, kind of working through PEMDAS. 4 minus 12 is going to give us -8. And I have -4 minus the absolute value of -8 is equal to -12. The absolute value of -8 is actually 8. So we have -4 minus 8. I want to know if that's -12. And luckily for us, -4 minus 8 is -12. So k equals 12 is truly a solution here. Let's go ahead and check it again, but for -4. And just because I'm running out of space here, I'm just going to erase all of this. and plug in our -4 case. Now, you guys don't have that luxury, so make sure that you write down it exactly the same as it was, and we have a -4 in there. So -4 minus the absolute value of 4 minus -4. Okay, so remember this is 4 minus -4. Minus minus becomes plus plus. So 4 plus 4 gives us 8 when we're simplifying that. The absolute value of 8 is obviously 8, so -4 minus 8 is that -12, and we just did that. So we can see that -12 is -12. So our solutions are k is equal to 12 and k is equal to -4. Or if you're fancy schmancy and practicing, this is really k is equal to -4, comma, 12. There are two solutions. The smaller solution comes first in our set builder notation. All right. Next problem. Absolute value of r minus 2 plus 5 is equal to 6, okay? So this is in like the standard way that you would write an equation. The past two, we had values and numbers on the left side, and that's a little weird. But here we can clearly see that we have an absolute value plus 5 is equal to 6. So step 1 says that we need to isolate our absolute value. So we're just going to subtract 5 on both sides. We have the absolute value of r minus 2 equals 1. Once I am completely isolated like I am now, we can consider our positive case. Add 2 to both sides. And then we can consider our negative case. R minus 2 is equal to -1. Add 2 to both sides, you get r is equal to 1. -1 plus 2 is +1. Step 3 says to check for extraneous solutions, and also that's what the directions say too. So r minus 2 inside of a parentheses plus 5, is that actually equal to 6 is what we want to see. So I'll plug in my -1 first. 1 minus 2. Simplify this. This gives us the absolute value of -1 plus 5. Is that equal to 6? Absolute value of -1 is 1. 1 plus 5 is certainly equal to 6. Yay! And check our second solution. R minus 2 plus 5, is that equal to 6? And we're considering the case when r, our input value, is 3. 3 minus 2, again, we're going to simplify the inside. That's the absolute value of 1. Plus 5, is that equal to 6? And of course, the absolute value of 1 is just 1, and 1 plus 5 is 6. So both of these, r equals 1 and r equals 3, is our solutions, or you can write r is equal to 1 comma 3, where 1 comes first inside of our curly braces. Yay! Okay, so hopefully you're feeling good about how to solve absolute value equations. Now let's go into solving absolute value inequalities, which is almost exactly the same. Remember, there's 3 steps to solving absolute value inequalities. Step number 1, isolate your inequality. Step number 2, consider your positive and your negative case. Step number 3, graph on a number line. Then it's going to want us to give the domain in interval notation and set builder notation. So since this problem, it has the number line, I'm just going to rewrite it below so I can use that number line. Absolute value of b plus 5 is less than 8. Step 1's complete because the absolute value is alone. It's isolated already. So our positive case says b plus 5 is less than 8. We're going to subtract 5 on both sides. You get b is less than 3. And since I have b is less than 3, I'm just going to graph it right now. I'm going to find the number 3, and since it's less than, it's going to be an open circle. So here's 3, open circle, and I'm going to shade any values less than 3. Anyway, in this direction. I'm going to solve my negative case. B plus 5. But what happens when you multiply or divide by a negative? You have to switch the sign and change the right-hand side. So B plus 5 is greater than negative 8. Subtract 5 on both sides. You get B is greater than 8, negative 13. So B is greater than negative 13. I can graph. There's an open circle at 13, open circle, and B is larger than 13. So that means everything bigger, right? Or everything going this way. Then I only want the parts where my graph overlaps. I only want the parts of my graph where they overlap, right? So really, I only want this part of my graph right here, in between negative 13 and 3. Just this part, not in either direction. I know they still continue going on, but I do want my open circles at negative 13 and 3 and shaded in between. Cool. Then it wants us to give the domain, right? So right now we have the domain in our interval notation, right? That's in interval notation. Now we want to describe the domain in, I'm sorry, that's not interval notation. That is inequality notation. I want to put it in the shorthand, which is the interval notation. So remember, this direction is negative infinity on our number line. This direction is positive infinity. At negative infinity, I am not shading, so I'm not starting. And the first part where my graph actually begins is right here at negative 13. And since negative 13 was not included, B has to be greater than negative 13, and there's an open circle. I'm going to use an open parentheses. And then I can see that my graph is being shaded all along in here. And my graph keeps going and going and going until the number 3. I have another open circle, which means I have an open bracket. So this means, remember, domain is x values. So the x values for this graph exist from negative 13 to 3. Doesn't actually include negative 13 and negative 3 because we don't have greater than or equal to or less than or equal to in our inequalities. We also want to come up with our set builder notation for our domain. And so remember, it's always x such that x is an element of the real numbers, but we want to just take our inequalities. Like x can be any number, all numbers in between, but B has to be greater than negative 13 and B has to be less than 3. Otherwise, we'd be including the entire number line if we just said all real numbers. Those are really bad curly braces. There we go. So this describes the domain where all x values exist for this inequality. This describes the domain for all x values that exist for this inequality. And our fancy set builder notation also denotes the same. Let's do another. All right. In a day. Oh, you know what? It's because I'm not on the mouse. Here we go. Absolute value of 7p minus 4 is less than or equal to negative 25. I'm going to rewrite it again. Absolute value of 7p minus 4 is less than or equal to negative 25. And it is isolated. So I'm going to do my positive case. 7p minus 4 is less than or equal to negative 25. And I want to solve for p, so I'm going to add 4. I'm going to have 7p is less than or equal to negative 21. Divide by 7. And I get p is less than or equal to negative 3. Cool. So I can graph right away. Once I've gotten my positive side, P is less than or equal to -3. So let's find -3 on our number line. And since it's less than or equal to, we have a filled in dot. And I want P is less than or equal to -3. So pick a number less than or equal to -3, and maybe that's like -10. Shade in that direction. So I'm going to shade off that way. Oops. All the way towards -infinity. Then I'm going to solve for my negative. I have 7p minus 4, the inequality or the absolute value stays the same. But when you multiply by -1 to your inequality, you have to change the direction. And the other side is going to become 25. We're still going to add 4 to both sides. Oops. I'm going to have 7p is greater than or equal to 29. Divide by 7. Divide by 7. I get p is greater than or equal to 4.14. 4.14. And then I'm like, okay, here's 4.14, I guess. It's greater than or equal to, and shade. And yeah, you can solve stuff. But let's take a second and look at this original problem, which we should have done at the beginning, really. All right, I have an absolute value less than or equal to a negative number. This will never happen. We will never have an absolute value equal to a negative. So although I'm algebraically able to solve for the solutions, there's really no solution to this problem because this will never, ever exist. Although I can algebraically find them, I can find them with algebra. We just did. We have to always make sure when our absolute value is isolated that we make sure that it's not equal to a negative number because that's never going to happen. So although we could find the numbers 4.14 and -3, this problem is actually no solution. Careful on that. Maybe ask yourself before solving if it has a solution or not, if it's possible. Instead of getting through all that work like we just did and finding out that you can't. All right, but remember, it's once it's isolated. Once it's isolated. Okay, here's our next one. The absolute value of b plus 5 over 9 is greater than -5. All right, greater than -5. I want to isolate my absolute values. I'm going to multiply by 9 on both sides. I have the absolute value of b plus 5 is greater than -45. All right. So remember, it can't equal it. It cannot equal a negative number once we get to this spot right here. We cannot equal it, but this one just says it's bigger than a -45. This one just says it's larger than. So we do need to check. We can split it into our positive side. B plus 5 is greater than -45. -5, -5. You get B is greater than -50, which is like way down here. Let's make this -50. And it says it's greater than. So we're shading all the way in this direction. And let's check the negative. It would be b plus 5 is less than 45. This negative gets multiplied to that, changing the direction of the sign, and a negative times a negative becomes a positive. This leaves us with b is equal to 45 minus 5, 40. Oops. B is less than 40. So let's find a number line all the way over here at 40 and open circle, and it's less than. Woohoo! So this is pretty much the entire number line covered. Entire number line covered. Okay, so like we said, B is less than 40 and B is greater than -50. And we can see like the sketchy number line I put underneath. 40 is all the way on the positive side, -50 is all the way on the negative side. They have open numbers and they're shading and realistically like overlapping each other. And in class we said like, oh, we're gonna only include the areas that overlap. But let's take a good look at this statement right here. Absolute value of B plus 5 is greater than -45. This is always true because absolute value will either give us a positive value or like maybe 0. So since it's always true, our entire number line from -infinity to +infinity is colored in. Every value of n will always give us a true solution because of the way absolute values behave. And so we're going to say our solution is all real numbers. All real numbers. And so our domain, if we're talking about all real numbers, in inequality notation, or I'm not, sorry, not inequality notation, in our interval notation will be from -infinity to +infinity, because this number line goes towards -infinity. This one goes towards +infinity, and it's all covered. Or our set builder notation will say x such that x is an element of the real numbers. There's no like inequality that's going to be false there. So we can just leave it with that beginning statement that we always make with our set builder notation. So the last two examples have been pretty tricky. We've got to be careful and watch out. Once we isolate our absolute value, is that going to give us a statement that's always true? Then it's all real numbers. If it's never true, then it's no solution. Let's try our last problem and see what we get. So number 10, the absolute value of -4n plus 3 plus 2 is greater than or equal to 5. Let's go ahead and isolate our absolute value, being careful of what that statement gives us. So I have the absolute value of -4n plus 3 plus 2 is greater than or equal to 5. We want to subtract 2 on both sides. So we have the absolute value of -4n plus 3 is greater than or equal to 3. So far, we're in the clear, right? We don't have an absolute value that's greater than a negative number. That would always be true. And we don't have an absolute value less than 0. It's less than a negative number. That would never be true. So we are golden. Let's go ahead and solve for the positive. That would be -4n plus 3 is greater than or equal to 3. We're going to subtract 3 on both sides. Get -4n is greater than or equal to 0. Divide by -4. Remember, dividing by 4 is okay. Having a 0 in the numerator is okay. We end up with n is greater than or equal to 0. So on my number line, we'll find 0. Greater than or equal to means not only do I have a circle, but it is closed. Greater than or equal to. And numbers greater than or equal to is like numbers like 5 or something like that. So I'm going to shade in this direction all the way till +infinity. I also want to solve for the negative side. So -4n plus 3 is less than or equal to -3. Remember, we have to flip the sign and change it from positive to negative. We're going to subtract 3 still from both sides. We have -4n is less than or equal to -6. Divide by -4. We have n is less than or equal to 3 halves. +3 halves. which is 1.5. N is less than or equal to, I'm sorry, yeah, 3/2. And you know what? We made another mistake. That's all right. Mistakes are normal. Remember, when we, check this out. Oof. This is a good problem, divided by -4, and we have an inequality, we have to change the direction. So not only did we have to change the direction when we first changed it to the negative case, but we divided by negative again. So this is really n is greater than or equal to 3/2. N is greater than or equal to 3/2. And you know what? We did the same thing over here. We divided by -4 and we did not change this sign. So we better do that. Less than or equal to 0. That changes things. So let's go back and graph. N is less than or equal to 0. Find 0. It's closed. But remember, we had to switch. It's less than. So we're going to shade this direction forever towards -infinity. And then for n is greater than 3/2, greater than or equal to 3/2. 3/2 is like 1.5. That's like right here. We're still going to have a closed circle. Try my best to make a closed circle. And we want numbers bigger than or equal to 3/2. So like 2, 3, 4, all of those values. And we're going to shade all the way towards positive infinity on that. Woo! We got to be super duper careful on that. Again, we have our domain. We have it in our intervals right here. I mean, inequality. That's our inequality notation. And we want it in our interval notation. So going from the left side of our number line way down here at -infinity, it is existing. And our graph continues all the way up until 0. There's a small gap, so we're going to put our union symbol, and then it begins again at 3/2 and continues all the way towards positive infinity. Now, actually, the 0 and the 3/2 are included. They are closed circles, so they should have closed brackets. They have closed circles. They should have closed brackets. They are greater than or equal to and less than or equal to. And lastly, in our set notation, we would say x such that x is an element of the real numbers, but n is less than or equal to 0 and n is greater than or equal to 3/2, since those were our two inequalities that we solved for. This n is greater than 0, or n is less than or equal to 0. That was our positive case right here. And n is greater than or equal to 3/2. That was our negative case. Okay, number 11. Solve each compound inequality and graph its solution, then give the domain, an interval, and set builder notation. So this is an or inequality. You solve them separately. You can go to bed, or you can go to bed early, or you can go to bed late. You cannot do both at the same time. So -2x is less than or equal to -6, or -5x is greater than 15. I'm going to divide both sides by -2 on the left. And we're not going to make the same mistake we did last time. We are going to change the direction of the symbol of our inequality, -3. Or do the other one. Negative 5x is greater than 15. We're going to divide by a negative on both sides. And whenever we multiply or divide by a negative, we have to change the direction of the sign. All right. So we have x is greater than or equal to negative 3, or x is less than 3. All right. And we get to just graph these as is. I'm going to graph this one in pink. X is greater than or equal to negative 3. Let's find negative 3 on the number line. We're going to color that dot in since it's greater than or equal to. And x is greater than or equal to, so we're going to shade in directions that are greater than or equal to, like the number like 6 is greater than negative 3. And this goes all the way towards positive infinity. The next one we have is x is less than negative 3. So negative 3, x is less than oops, this should have been positive 3. What a knucklehead. This should have been positive 3 because a negative divided by a negative is a positive 3. Oops. So we have positive 3, closed circle. 6 is still bigger than positive 3, so we're shading in this direction still towards positive infinity. 15 divided by negative 5 is still negative 3. At negative 3, we're going to have an open circle. And any number smaller than negative 3, like negative 8, we're going to shade in that direction all the way towards negative infinity. All right. So our domain in our interval notation says our graph is shaded all the way on the left at negative infinity, and it goes up until negative 3. And it's less than negative 3. It's an open circle. We're going to have open parentheses. Then we have a gap. That's okay. Making our way downtown. Starts again at 3 right here and continues all the way towards positive infinity. But it's including the number 3. It's including it. It has a closed circle, so I should have a closed bracket. And lastly, our set notation should say x such that x is an element of all real numbers, but x has to be smaller than negative 3, and x has to be greater than or equal to positive 3. So we can't have any values of x in between negative 3 and positive 3. Like 0 will give us a false statement. 0 is not a solution for this. Same with like negative 1 or positive 1. Those numbers don't work. Everything in the gap, everything right over here that is not included in this will give a false statement if we plug it in. So those are not solutions. That's why we don't include them in our set builder notation. That's also why we don't include them over here. That union part that says like nothing else except for these 2 intervals that I give you. Okay, and let's do the last one. I think it's going to be an and compound inequality. Nice. So we have, it doesn't say the words and, but notice that it has negative 83 is less than or equal to 7x plus 1 is less than negative 27. It's all combined together. The thing that they have in common, because and compound inequalities have things in common, is put smack dab in the middle right here. And that's also where we want to draw our attention to isolate the variable, in this instance, x. So how can we get 7x plus 1 to just be x? Subtract 1 from all sides. Whatever you do to one side of the inequality, now we have 3, do them to all. So we have negative 84 is less than or equal to 7x is less than negative 28. Now I still want to get x alone, so we're going to divide all sides by 7. negative 84 divided by 7, hoping that divides nicely. Yep, you know what? It's 12. Negative 12 is less than or equal to x is less than. And 28 divided by 7, negative 28 divided by 7 is also a nice number. It's negative 4. So we have negative 12 is less than x, and x is less than negative 4. Remember, this is an and inequality, so really you can think of it as this being the first one. X is greater than or equal to negative 12. And x is less than negative 4. So you can graph both of those. So x is greater than or equal to negative 12. Let's find negative 12 on here. Close it because it's greater than or equal to, and we're shading all the way to the right for that one. But we also have x is less than negative 4. So here's negative 4. It's just an open circle and it goes all the way to the left. On our compound inequalities. Oops, why does it do that? Okay, on our compound inequalities. For compound inequalities, we only want the overlap. So that's right here. Compound inequalities want the overlap. So there we go. And if we were going to denote our domain, we have it with our inequalities already, but we want to do it in interval notation. They do not overlap all the way down here at negative infinity. They don't. It doesn't start the overlap until negative 12. And negative 12 is a closed dot. That's why I put the closed brackets, the square brackets. My graph continues living here, keeps going all the way up to negative 4. But negative 4 has an open circle, meaning I'm going to have my open parentheses. And that's all my domain is. In our set notation, we're going to say x such that x is an element of the real numbers. And you can separate your two inequalities if you want, or you can just write negative 12 is less than or equal to x is less than negative 4. Write them combined just like it is right here. You can plug that into your set builder notation. Alrighty, I hope that this review helped you in some way, shape, or form, and I will see you in class tomorrow.